Okay, welcome back. Here's where we go through another video where I'm going to talk about the steps to actually perform the elimination, and then like I said, I'll go through an example. So Gaussian elimination is the term for reducing a matrix to row echelon form. So the first step is find the first non-zero column, and this is going to be your first pivot column. Right? So the idea being that although we almost never work with them in this class, right? If you're given a matrix, it's possible that all your you could have a column of zeros that starts the matrix. So we're looking for the non-zero column. Make the position at the top of this column 1. Right? Interchange rows if needed. And I say it needs to be 1 technically in row echelon form, right? It does not have to be 1. It could be a 2 or a 4, but our lives are going to be easier for it to be 1. So the most important thing is actually that it is non-zero. And you can interchange rows if needed. And I should say rather that should be your preferred first step. It's going to be a lot easier if you have a 1 somewhere else in this column to change your rows so that it's at the top, instead of, say, dividing by 7, where suddenly you have ugly fractions. And then step 3, use replacement to make all the entries under this pivot 0. Right, so we have our leading entry at the very top of the column, and then we'll use replacement to make everything underneath them 0. And then we just repeat 1 through 3 with entries below and to the right of this pivot. Right? So for example, suppose that I have this going on. What I'm saying is that, right, kind of if I think about everything that's left as a matrix, eventually what I want, right, is to perform steps 1 through 3 so that all this other matrix is performing the process, and so on and so forth. So that's how I will repeat those steps. And then once you've done that, you've got your matrix in row echelon form. Now, Gauss-Jordan elimination is what we use to reduce it to reduced row echelon form. So we'll start with the bottom pivot, right? So the pivot that's at the bottom and to the right, and make the pivot 1 by scaling, and then make the entries above the pivot 0 by replacement, and then go back up as we go. So oftentimes, because we do this kind of top to bottom, left to right, people will try to do Gauss-Jordan elimination, in other words, reduce it all the way by doing top to bottom, left to right, and our lives are actually much easier if we start at the bottom and go up. And you'll kind of see why in the example we're going to go through. Let's get started. Okay, so suppose I have this system, right? 2x1 minus 5x2 plus 5x3 equals 17. x1 minus 2x2 plus 3x3 equals 9. Negative x1 plus 3x2 equals negative 4. So this gives me the following augmented matrix. And I say recognize my first non-zero column. So step 1's, very straightforward. Ta-da, we did step 1. So step 2, I'm going to get that 1 up at the top, right? And I just did that by switching row 1 and row 2, right? And it's important to note, I don't think I mentioned this in class or anywhere else. From now on, this is row 1, right? Like these rows, row 1, row 2, row 3, aren't set throughout the whole matrix, right? Like I made row 2 row 1, and now this is row 1. So step 3, I'm going to make these terms 0. So if I do row 2 minus 2 times row 1, 2 minus 2 is 0, right? And then negative 5 plus 4 is negative 1, right? 5 minus 6 is negative 1, right? 17, right, minus 18 is negative 1. Likewise, if I do row 3 plus row 1, right, 0, 3 minus 2 is 1, 0 plus 3 is 3, Negative 4 plus 9 is 5. Okay, so that was where we ended up. Have to have space to keep going. But now, like I said, so we're here, and then we just repeat. So I want this to be 1. Now I can do this by switching rows, however, this is a pretty easy scaling, right? Negative row 2, boom, I've got my leading 1s. Row 2 plus row 3, right? So that's going to be, right? Now it's important to note this, right, whenever I'm doing these operations, is referring to that row 2, not this one. It's always referring to the matrix you were doing before. And like I said before, when in doubt, do one step at a time. So, right, negative 1 plus 1 is 0, negative 1 plus 3 is 2, negative 1 plus 5 is 4. Right? So technically this is in row echelon form. Here I took it one step further and just divided everything by 2, or multiplied it by the scalar 1/2. So 0024 becomes 0012. So I'm in row echelon form. And you can see that, right? So this corresponds with the system of equations x1 minus 2x2 plus 3x3 equals 9, x1 plus x3 equals 1, 2x3 equals 4. So, right, this is a very solvable system, and we can work with that. However, if we get it into reduced row echelon form, our lives are actually even easier. So if it's in reduced row echelon form, to make that happen, remember, I'm starting with the bottom pivot, right? So I'm actually thinking about this one, and I'm going to use it to make all of this 0. And the way that I do that, right, is row 2 minus row 3. Right? So the reason that that's so nice is because you have all of these zeros in front of it, right? So you're not messing with or changing any of this stuff. You're just changing the last column of my variables, and then I have to also account for what's happening over here on the other side of the equal sign. Right, so 1 minus 1 is 0, right? 1 minus 2 is negative 1. Right? Row 1 minus 3, row 3. So to get this 0, so 3 minus 1 is 0. 9 minus 6 is 3. And then I do the same thing, right? I'm trying to get rid of this. So row 1 plus 2, row 2, right? So that's 0. This was already 0 because like so, and that's why it's, like I said, that's why it's really nice to start at the bottom and then work your way back so that you don't have as many things to deal with. And then, right, 3 plus 2 times negative 1, 3 minus 2 is 1. And so now we're in reduced row echelon form. Right? So I've got a leading pivot, zeros, a leading pivot, zeros, a leading pivot, zeros. These are non-zero, but there's no leading pivot, so that's not a problem. And notice that this is a very nice system, right? So x1 equals 1, x2 equals negative 1, x3 equals 2, right? And because we're all excellent at algebra, we are able to solve this system, right? And we know that, right, it is solved. And that's all I have for you. So that's an example. There's going to be some WebAssign homework following up with this. And again, the book has a ton more examples. Their writing and graphics are much neater than mine. So if you need more than just this one, go ahead and take a look at some of those. And hopefully as you practice on the WebAssign, it should become clearer. That's all I have for you. Have a nice weekend. Until next time.